Hey everyone, today I want to talk to you about how we can defend distributed systems embedded in things like factories, planes, trains, and automobiles from attacks with a new approach called bounded time recovery. I've been working on this with Ida Roth, Brian Sandler, Andreas Heberlin, and Lin-Tei Suong-Tan. In this work, we focus on cyber-physical systems, which are distributed systems that use data from a set of sensors to change the behavior of a set of actuators. As a quick example, let's take a look at this chemical vat. There's two sensors attached to it, a temperature gauge and a pressure gauge, and there's a couple of actuators that act on it. A burner, which can add heat, a pressure valve through which chemical can flow in or out, an emergency alarm indicator, and a live stream data monitor. The set of sensors and the set of actuators are connected together by means of a set of control nodes. In these control nodes run applications. So we have data, for example, coming from the pressure gauge, going through a control node, and changing the behavior of the pressure alarm. And similarly, we have other applications in which data goes from the set of sensors through to the set of actuators. CPS face a problem similar to that of traditional distributed systems, in that they can be attacked. For example, in this topology, let's say an attacker compromises node 4. In this setting, the attacker is able to modify the data that's being sent out of task number 3 so that it can change the behavior of the burner. If it increases the burner flame, then it could eventually cause a catastrophe to occur. So we see that cyber-physical systems need fault tolerance for more than simple crash faults. One option to defend CPS against attacks is to use a BFT protocol, which has the advantage of being able to completely mask faults. However, there's a substantial cost to implementing BFT because we always need at least two F+1 replicas to tolerate F faults. However, cyber-physical systems often use relatively simple CPUs and operate in power or space-constrained settings, so it becomes difficult to meet all of the requirements of BFT. For instance, if we were trying to use BFT in our example from the previous slide, we would need to schedule all of the replicas shown in gray. Only a subset of those replicas are actually schedulable, so we wouldn't be able to run all of the applications that we want to in our system if we were to use BFT. So what else can we do? Well, many cyber-physical systems do not actually need to perfectly mask all of the symptoms of a fault. Let's take a quick look at our burner application again. At normal times, the burner will be kept at a constant flame setting, so the temperature will be in a relatively constant temperature range. However, when a fault occurs, the burner flame increases, which causes the temperature to continuously increase up until a point at which some kind of catastrophe might occur. After the catastrophe occurs, the system is non-recoverable. However, the period of time between when the fault occurs and when the catastrophe occurs is what we call a recovery period. That is, the system can be recovered to a correctly operating state so long as the recovery occurs during the recovery period. And hopefully, we can leverage this period of time to create a fault-tolerant solution that is less resource intensive. Now, the exact period of time that we have available for recovery varies by systems, but for the ones that we've looked at, the recovery period seems to be long enough that recovery is possible. So our approach in this work is to provide a guarantee we call bounded time recovery, which basically says that the system will always provide correct output so long as there's no fault within the past t seconds. So if a correctly operating system experiences a fault, we have a deadline of t seconds past the occurrence of the fault by which to have recovered the system. The recovery can occur at any point before the recovery bound has elapsed. After we have recovered the system, we will resume correct operation. So how can we actually guarantee that we will recover in bounded time? There's two main pieces to this puzzle, the first of which is detection, in which we use F+1 replicas to recover from up to F faults. The second piece is recovery, in which we reconfigure the system so as to continue to operate correctly. In our simple running example, let's take a look at some set of tasks running on the nodes and some set of replicas that are also running on the nodes. We'll take a look at a particular data flow, that going from task number 4 running on node 1 to the task number 5 running on node 2 and the replica of task 5 running on node 4. If the attacker compromises node number 2, then the task number 5 running on node 2 will stop operating correctly. However, because we have a replica running on node 4, it can catch when the adversary causes any externally visible effect. Once we have caught the adversary, we need to change or reconfigure the system. What this involves is migrating the tasks to currently healthy nodes and reconfiguring the data flow. Providing the bounded time recovery guarantee is non-trivial. First, we need to identify when a fault occurs so that we know by when we need to complete recovery. We also need to identify which node is faulty so that we can recover the system to a correct state. At the same time, we need to prevent issues like incorrect attribution, in which a node believes that another healthy node is faulty instead of the actually compromised node. We also need to prevent false negatives, in which adversaries could work together to make the system believe all is well when, in fact, there are compromised nodes present. We also need to prevent false positives, in which there are no faulty nodes in the system, but a healthy node believes another node to be faulty. All of this we need to do while ensuring we can guarantee that we will have a bound on the detection and recovery time, even if an adversary tries to delay the detection or recovery of the system. Now that we've talked a little about the basics of cyber-physical systems and bounded time recovery, let's talk a little bit more about some details. First, let's talk a little bit about our model. We assume that all faults are observable Byzantine faults, meaning that there is some kind of externally visible effect of the fault. We won't try to handle bit flips in some obscure node's memory that will never affect anything. We also assume our system is synchronous, meaning that continuous time can be divided up into discretized rounds. Our system does not need to have all-to-all connectivity. As is common in CPS, we can work with a combination of point-to-point links and buses. The maximum number of nodes in our system that can fail is one less than the total number of nodes. And finally, we have a mixed criticality system, meaning that we have some applications that are most important to keep running and some that we can drop when we don't have enough computational resources to run them. In our approach, the system operates in a mode that is stored in a mode tree. At outset, the system operates in a root mode with no faults present. This corresponds to a direct mapping of tasks to specific nodes on which they will run. When an adversary compromises a node, let's say node 2, this triggers a mode transition. What this means is we will read in a new mapping of tasks to nodes. And since everything was originally running in a different place, we may need to migrate tasks to their new assignments, in the process perhaps dropping the least critical application. If now the adversary additionally compromises node 1, then we will read in the new mapping and perform task migration, again possibly dropping the least critical application. This raises the question of how we actually catch a fault in order to trigger a mode transition. We need at least one node to be operating correctly to be able to catch the fault. So if there can be up to F faults in the system, we need at least F+1 replicas to be able to catch that fault. Let's take a quick look at an example. Here, task number 5 is running in two places, one on node 4 and one on node 2. Both copies run the same exact program, taking a set of inputs to an addition function and producing an output. The two replicas will cross-check one another's behavior to catch when the other one becomes faulty. So for instance, if node 2 is compromised, the attacker may change the output to not match what the addition function should have outputted. Node 4, having cross-checked what node 2 is doing, will be able to catch the fault. However, it's not quite so simple. Let's say node 3 is compromised, and node 2 is running a replica task that catches node 3 misbehaving. At this point, node 3 can simply make a counterclaim that node 2 is misbehaving. So, how do we resolve this discrepancy? We require all messages to be signed. So, if both the task running on the faulty node and its replica receive a signed input, they will both also produce a signed output. The replica task will compare the signed output that it produced to the one that node 3 produced. If they do not match, this constitutes evidence of misbehavior, and node 2 is able to generate an evidence message that it can then distribute to other nodes in the system. So far, so good. But what about omission fault? After all, replicas cannot verify that a message was not received by another node. Our solution to this is to allow a node to unilaterally declare a particular link to be faulty so long as it is one of the endpoints of that link, and it signs its link fault declaration. Let's take a quick look at an example. Here, let's say there is a data flow moving from task number 1 to task number 2 that goes through an intermediate node. If the intermediate node is compromised, the compromised node might omit forwarding the data from the task 1 to the task 2. When this occurs, the node that task 2 is running on might declare the link to the intermediate node as faulty, and we trigger a mode transition in which the data is rerouted through another node. Notice here that the adversary is limited in how much damage it can cause because it can only declare those links it is an endpoint of as faulty, which will only trigger the system to reroute traffic to other healthy nodes, so we're always making progress. Now, we still have some complexities to address. For instance, what happens when compromised nodes start to work together? Let's take a quick look at this linear topology. Here, time goes along the vertical axis, which we divide into discretized rounds. In round 0, we expect node 1 to send data to node 2, and we expect node 2 to forward that data to node 3. If node 1 is compromised, it might omit to send that data to node 2. In this case, node 2, instead of sending data to node 3, will send a link fault declaration. However, if node 2 is also compromised, it may try to protect node 1 by omitting to send the link fault declaration. However, node 3 knows that something is wrong because it knows that by the end of round 1, it should have received either the data from node 1 or the link fault declaration from node 2. Now, this might seem simple, but there's a lot of additional complex strategies that an adversary might employ. For instance, node 2 might claim that it is in a different mode than node 3 and did not need to send either the data or the link fault declaration to node 3, and we still need to handle that. But we don't have enough time to get into it, so you can read more in the paper. Barring these complexities, we can summarize our approach as asking what should have happened before. That is, if a node is currently in round 2, then it will wonder what should have happened in earlier rounds in order to reason about which nodes and links are currently healthy. Another aspect of ensuring correct operation of the system is making sure that all nodes know when any other node in the system fails, because otherwise the mode that the nodes are operating in will diverge. In our example, let's take a subset of the applications we initially talked about and schedule a few replicas for them on node 2. If an attacker compromises node 4, then node 2 is able to detect that node 4 is faulty and trigger a mode transition. But since node 1 was never running any task or replica for the orange application, it will not participate in the mode transition and continue to operate in a different mode than the rest of the system. Our solution to this is to have all nodes send a periodic heartbeat message to all other nodes in the system. However, we need to ensure that attackers do not forge these heartbeats in order to trigger mode transitions that should not have occurred. So, we require all nodes in a periodic manner to send a heartbeat message in which the content is a signed opinion of what mode that particular node thinks the system is currently in, where a mode consists of the set of nodes and links that is considered to be faulty. There's quite a few elements of our approach that we will not have enough time to get into, but you can read more about them in the paper. We will have enough time to get into one of the optimizations that we use, using multi-signatures for scalability. Multi-signatures allow sets of nodes to sign messages. They are of constant size and they require constant time to verify. This could be useful in our approach. What we've described so far requires many messages to be sent around, but the message content is often the same. For instance, let's say node 1 generates a heartbeat message and signs it. It sends copies of this message to all of its neighbors. The neighbors will log this message and then also forward it to node 5. Node 5 also logs these messages and is responsible for signing each message and forwarding them to node 6. If instead we were to use a multi-signature approach, we could have taken these 3 messages with identical content and generated a single message using multi-signatures, which has all 4 keys represented, and then forwarded the single message instead of 3 messages. This is particularly useful in large topologies. In small topologies, it is not quite as useful because multi-signatures require a longer time to verify. However, since the verification time is constant, the advantage of using them grows more and more as the system size grows. Now that we've talked about how our approach works, let's look a little bit at the results that we've obtained from experiments. Now there's quite a few experiments that we ran, but we don't have enough time to talk about them all, so we'll limit ourselves to discussing a few key results. First, let's talk a little bit about the costs of using REBOUND. For this experiment, we used synthetic workloads applied in randomized network topologies and compared REBOUND with and without multi-signatures. First, we'll look at the unoptimized case without multi-signatures. In absolute terms, the cost is still manageable. For instance, in the leftmost graph, the cost per link per round is still under 20 kilobytes for a 100-node system. Second, we see that as the system size increases, the cost of using unoptimized REBOUND does increase. When we display the full version of REBOUND with multi-signatures, we can see that there's a huge scalability improvement for resources consumed. And the differential between the two approaches only grows as system size increases. So the takeaways here are that the overhead is manageable and that we can greatly improve the scalability of REBOUND by using multi-signatures. Next, we'll take a look at our running example implemented in a real embedded platform. Here we see an oscilloscope reading for when a fault occurs in this real embedded platform. The vertical red line represents where the fault occurs. Each of the individual colored lines represents a PWM output used to control a specific actuator. When the adversary compromises node 4, they change the pressure alarm PWM signal to be a garbage value, and since there's no protection in this version of the system, no recovery occurs. In contrast, let's see what happens when we use REBOUND. The fault occurs at the same place in time, but after only a brief period, the system resumes correct operation and the pressure alarm no longer receives garbage PWM values. In the process, we had to drop the monitor application. But remember, since we have a mixed criticality system, it's okay to drop the least critical application in order to ensure the most critical ones are still schedulable given the more limited computational resources that are available. The takeaway here is that we have an approach that can both detect and recover quickly in a real embedded platform. In summary, we've introduced the concept of bounded time recovery, or BTR. BTR is a new approach to defending distributed systems against attacks that is low cost. It only needs F+1 replicas to tolerate up to F Byzantine faults. BTR guarantees that in bounded time, the system will detect and recover to a correct state. This is a good fit for cyber-physical systems because CPS are often resource constrained and they don't often need complete fault masking because they have properties like thermal capacity or inertia that we can leverage. REBOUND is the first concrete algorithm to use a BTR approach to protect against Byzantine faults. It uses a multi-mode system so that when a fault occurs, the set of nodes in the system can transition between modes in response to the fault. By doing so, REBOUND is able to keep the most critical applications running because it can migrate the tasks of the critical applications to healthy nodes, in the process perhaps dropping the least critical ones. Thank you.